Welcome back to another comparative teardown of defect power supplies. This time I have for you two wall warts that came with two 3.5-inch HDD enclosures. In the previous comparative power supply teardown, we had a look at two defect power bricks that came with enterprise SDSL communication boxes. Card here, link in the description. Now, this is obviously consumer stuff, so I do not expect much. But anyway, enjoy! Let's first talk about the lifetime of these things, respectively. Well, not quite the mean time to failure, but at least the time to failure. Because I had both of them in use and I have hard data for that. I bought two of these Zalman external HDD cases in December 2012. And I had always one of the power bricks, which I used up consecutively, running 24/7. And the last power brick failed in August 2021. That's a total of 104 months, or on average, one of these power bricks that came with the Zalman cases lasted for 52 months. When the last of the Zalman power bricks died, I bought Fantec external HDD cases. That was, of course, also in August 2021. Cards here, links in the description. And now the first power brick from that pair, which also was in operation 24/7, just died in December 2024. That is after just 40 months, 12 months less than the Zalman wall warts. I should mention that the external enclosures from Zalman, which are very solid and nice, are still going strong to this date. The reason I bought the Fantecs was that I suspected the enclosures to be defect. Reason being, if you measured the wall wart without load, it gave off 12 volts with very little ripple, so it looked good. However, if you actually put load on these things, the voltage breaks down. Now for a closer look onto these two dead wall warts. They are both made in China, of course, and the Zalman one is made by Power-Tec, while the one that came with Fantec is not branded. Both feature an input voltage range of 100 volts to 240 volts at 50 to 60 Hertz. However, the Zalman unit has a peak input current of 1.5 amps, while the newer one here, almost 10 years newer, only draws a maximum of 0.8 amps. So that one here obviously has an inrush current limiter or something, and maybe even a power factor correction, which wasn't a big thing 10 years ago. The Fantec one delivers 12 volts, 2 amps, so 24 watts. And the Power-Tec one, delivered with a Zalman, delivers 12 volts, 1.5 amps, so 18 watts. The Fantec one is a little bit sparse when it comes to the proof marks, but it has the CE label. So has the Power-Tec one, but it also has here a proof mark from some German institutions. And most importantly, it has these two rectangles here, meaning it's a doubly isolated unit, meaning it doesn't need a main earth connection to work properly. And you notice the absence of that little icon here on the unbranded one. On the top side, the Power-Tec one that came with the Zalman, yeah, it's just labeled, while at least the unbranded one features a power LED, which we will see in action later on. When it comes to the cable, both have a ferrite core here for filtering, but the cable of the Power-Tec unit is a round one with 2 wires inside, quite massive, while the one from the unbranded wart is, just 2 strands side by side, quite flimsy affair. When it comes to size, the Zalman unit from Power-Tec is smaller. It's about 41 millimeters by, let's say, 68 millimeters by 28 millimeters. The considerably larger unbranded unit that came with the Fantec is about, let's say, 45 millimeters, and in length, 91 millimeters, and thickness, it's a little bit curved, so let's take about the center, 34 millimeters. Talking about power density. So with our measurements here now in centimeters, the no-name wart comes to a volume of about 139 cubic centimeters, while the Power-Tec wart has a volume of about 78 cubic centimeters. If we divide the power output by the volumes, we come to a power density for the no-name of 0.173 watts per cubic centimeter, while the Power-Tec has a higher power density of 0.231 watts per cubic centimeter. That's a little bit against what I've observed previously with other wall warts and power bricks. Usually newer power bricks, and there are 10 years between them, have a higher power density. Because, well, in 10 years, the MOSFETs used for switching inside these things and the diodes and rectifiers and everything got better. So you have a higher efficiency and less waste heat. But not here. In addition, the unit with the lower power density, which should run cooler inside because more volume to dissipate the heat, only lasted 40 months, and the Power-Tec with older technology and higher power density made it to 52 months. Yeah. And now for the teardowns. I obviously had opened that Zalman unit before. Probably when I did the videos about the Fantec cases and did the failure analysis. Already counted, links in the description. So let's take this out, and I have no intention of repairing that old thing. So let's just, additional isolation material, always good. Can we get rid of that? Perfect. So mains AC comes in here, and we have here, I guess, a fuse or something. Yeah, that's a fuse. And then a MOF for voltage spike protection from mains AC, a filter capacitor, a common mode choke, and then this capacitor is in the way. Okay, and then we have can I get a better focus here? Thank you. 4 discrete rectifier diodes, another filter capacitor, and that big filter capacitor here has 400 volts, a 33 microfarad from Yalicon, And it's for a temperature range of 105 degrees. So that's good. What else do we have here? Nothing much. There is something hidden here in an isolation sleeve. Looks like another diode, but I want to be sure. Give me a second. Yeah, looks like another diode. Anyway, we have here yet another diode and yet another capacitor. That is probably the power supply for the controller itself. Let's see if we can find out something about that capacitor. So also 105 degrees, low ESR, and when it comes to the capacity, yeah, 22 microfarads, 35 volts. Okay, so there must be some mechanism to drop the voltage, because maybe that's in conjunction with the controller down here. But to get to that controller, we have to remove that heatsink. Okay, let's continue. We have here an X or Y. I always mix them up. Capacitor between the primary and the secondary side for EMI suppression. We have here an optocoupler over isolation slot going from the secondary side back to the primary side to the controller. And yeah, on that side, two big diodes and two capacitors and an inductor for output filtering. And please note that electrolytic is a little bit bulged, and that is also bulged, and that is also bulged. That's the reason while without load you get 12 volts out, and as soon as you load it up, the voltage goes to zero or near zero. Yeah, nothing much to see on that side anymore. So, and here on the back only some passives, resistors. But a nice isolation area, and here the isolation slot under the optocoupler for the feedback. Now I will try off camera to remove that heatsink here. Just a second. So that thingy here is a Zalman SD4844P. Current mode PWM controller with built-in high voltage MOSFET. Yeah, according to the data sheet, inside a power adapter that is in an enclosure, it's good for a 16 watt output. But that thing had to produce 18 watts. However, it's good for up to 21 watts in an open frame environment. I guess they just thought that, you know, putting a huge heatsink on it, it will be fine. Anyway, the built-in high voltage MOSFET has an RDS on, typically of 3 ohms. 3 ohms. That's a lot by today's standards. Let's crack the Fantec no-name adapter open now. I hope this will not give me any grief. Yeah, that seems to be easy enough. And here we go. And we have a lot of space. Why did that thing fail? But I can glue it together again. Maybe a repair will be possible. Anyway, let's get that board out. Okay, additional isolation material. And okay, let's start at the top again. So mains AC comes in here, and then we have here a fuse, which also is labeled here at the side as 10 ohms of 3.3 ohm, whatever. So this is also NTC, I guess, limiting the inrush current. Here's a position of a MOF that hasn't been populated. Then we have the first input filtering capacitor, which looks good. This is an inductor, but obviously just a single inductor as far as I can tell. Yep, just a single inductor. Yeah, there is place obviously for common mode choke, but they elected not to install that. Bigger filter capacitor, and on the feedback side we have another smaller capacitor. Then here the X or Y type capacitor across the isolation gap for EMI suppression. The optocoupler for feedback, the controller, and we have here a second X or Y type, it's a Y type capacitor for EMI suppression. The transformer, again, 2 rectifying diodes and 2 filter capacitors, which seem to be a bit bulged. And the indicator LED. Let's have a look at the back. Also, a nice isolation area between the primary and the secondary side. However, no isolation slot under the optocoupler. And I spot a little transistor here. So that's the feedback network driving the optocoupler. And on that side, I see some diodes and the bridge rectifier for rectifying mains AC and some resistors. And that's it. The big filter capacitor on the primary side is a 33 microfarads, 400 volts, and it's a ZSF vent for temperature range of, you can barely see it. Can you see it? Can I focus on that? Not quite, but it says 105 volts, so nothing wrong here. It's also not bulging. And the first capacitor here is, I have to change the focus. Yeah, that one is 105 degrees too. And can I have a value? 400 volts. Yeah, a little bit hard to read, huh? 50 microfarads, 400 volts. So they filter with a little one. After the bridge rectifier, then comes an inductor, and then comes the big one. And we have here for bootstrap, that is power supply to the controller itself, 10 microfarads, 50 volts, and some temperature, 105 degrees, also good. The output capacitors are both a little bit bulging, and they are both identical, I guess, 1000 microfarads, 16 volts, and also 105 degree types. Good. Now let's see if we can get some markings on that chip here. So the controller is a DM6359. It's of course also a current mode PWM controller with built-in MOSFET. According to the datasheet, for power supplies in the sub 28 watt range. Okay, we are pulling out 24 watts out of that thing, if it would be still working. And the RDS on of the built-in MOSFET is typically 2.1 ohms, so only a wee bit better than the controller in the Power-Tec unit. Yeah. Now, I promised I show you the power LED. If there's a loud bang now and the light goes out, I didn't put it back together accordingly. So, okay, something is wrong. Oh yeah, now you can see it. How it's pulsating. Yeah, it's not supposed to do that. That's it for today. Please note, both of these wall warts failed because some electrolytics gave up. And if we compare the old branded Power-Tec to the unbranded one, newer one that came with a Fantec, it's obviously they cut tremendously down on the parts count, but gave it a larger housing, which in the end, well, accomplished nothing. Anyway, till next time, bye.